My name is Lambertus Hesselink from Stanford University. It's a pleasure for me today to discuss with you the performance of the first digital holographic data storage system. This is an area of research in which we have been active at Stanford University for the past 12 years. Today I'd like to present to you what we believe is the first representation of digital data that has been recorded, retrieved, and then displayed. Holographic data storage systems are attractive for the potentially high capacity, on the order of terabytes, for their short access times, on the order of tens of microseconds, and their ultra-high transfer rates exceeding gigabits per second. Although there are now many applications that could benefit from such a system, its potential performance has not been realized because of a lack of peripheral components and roadblocks related to material performance and system integration. Recent advances in peripheral devices and improved performance of holographic recording materials, coupled with a better understanding of the underlying physical processes, have prompted us to demonstrate fully automated digital holographic data storage using a photorefractive volume recording medium. This first demonstration is necessarily limited in performance because none of the components have been optimized for this purpose. Therefore, we wish to chart a course of future improvements. The first demonstration was constrained by the availability of commercial components made for other purposes, such as a spatial light modulator for video projectors and a general-purpose charge-coupled device for image detection. In the first experiment, we have taken a still color image of a bird and digitized this with 8-bit resolution. The digital data are then holographically recorded inside a lithium niobate crystal using angular and spatial multiplexing. Upon storage of all digital data, the holograms are read out by using the appropriate reference beams. Finally, the color image is synthesized from the retrieved data and displayed on the video monitor. The optical arrangement used for this experiment consists of an argon ion laser beam that is divided into 2 beam paths, one for the object beam and one for the reference beam. The object beam, shown on the bottom of the figure, illuminates a spatial light modulator which impresses the digital data in page format onto the light beam in a checkerboard configuration of bright and dark pixels representing digital bits. This beam then passes through several lenses and a polarization filter to obtain the Fourier transform of the data page at the crystal face. The object beam spot size is approximately 1.5 millimeters by 1.5 millimeters in size. Simultaneously, the reference beam passes through spherical and cylindrical lenses to form a thin sheet of light about 2 millimeters by 10 millimeters in size, incident on the crystal at 90 degrees with respect to the object beam. The reference beam can be rotated in small increments to allow angular encoding of multiple holograms, and the crystal can be moved vertically to allow spatial multiplexing. In this manner, we can record 640 holograms, each in 4 different stacks or spatial locations. The experiment is controlled by a computer. During readout of the data, the reference beam is incident on the medium at the appropriate angle and location within each stack, thereby retrieving the recorded digital data page. Using a threshold operation, the optical signal is then converted into an electronic signal using a CCD array. With parallel readout of the CCD signals, very fast data rates can be achieved, exceeding 1 gigabit per second. The steps involved in restoring and retrieving digital data are now discussed. Although any digital data can be stored, we consider the example of an input image. First, the image is digitized and the bit stream is converted into pixel maps for input to the SLM. Second, the bit pattern or pages are recorded holographically. Third, the bit pages are retrieved holographically. Fourth, the color image is synthesized from these data and displayed on the video monitor. And finally, the original and reconstructed image are compared side by side. The first stored and retrieved image in a holographic data storage system is a bird having 240 by 180 pixels of 8-bit color. On the left-hand side of the image is the original color image, and on the right-hand side, the image after it has been digitally stored and retrieved from the holographic storage system. When comparing the image side by side, we note several pixel errors. although these errors have been made somewhat less obvious because of the limited resolution of the NTSC VHS video display. In the next experiment, we have transferred an image from the hard disk in digital format to the holographic data storage system. But this time we have added error correction coding to the recorded data to improve the bit error rate. In addition, we have implemented software corrections to reduce systematic errors resulting from mismatch between pixels on the SLM and CCD array. The next example we show is the picture of Kelvin having 88 by 99 pixels of 8-bit color. On the left-hand side of the display is again the original image, and on the right is the image of the file copied from the holographic data storage system. Using error correction schemes just described, we observe no differences. In fact, the image has been retrieved with 0 errors. In the next example, we have used a larger image of 240 by 180 pixels of 8-bit color. In this case, we need to store more pages of digital data in the holographic data storage system, making the retrieval of the image more vulnerable to errors. But also we were able to retrieve the image with no errors between the original image and the retrieved image from the holographic data storage system. In this demonstration, we have digitized a short video clip and compressed the data using an MPEG compression standard. These digital data are then encoded for later error correction and stored in the holographic medium. Upon readout of the digital data, error correction software is applied to reduce the bit error rate to make the data suitable for later video image decompression. A short clip is then displayed on the video monitor. The size of each frame is 120 by 100 pixels of 8-bit color, and 10 video frames are stored. The original video clip is again displayed on the left, and the video clip retrieved from the holographic data storage system is shown for comparison on the right. Again, no errors are visible in the video data, and the measured bit error rate was 10 to the minus 6. The principal limitation in performance of the demonstration system is the spatial light modulator. This particular spatial light modulator, which was taken from a TVT 6000 video projector, exhibits extensive electrical crosstalk between pixels. This means that when one pixel is turned on, the nearest neighbors are also turned on to some degree. In addition, the mismatch between the pixel format of the CCD and the SLM array requires that 128 pixels are used for each bit. Therefore, we have expressed the performance in terms of pixels and not bits. In this case, one bit is represented by 128 pixels. If we have an SLM that does not exhibit this crosstalk and which is matched to the CCD array in format, then performance is improved by 2 orders of magnitude in terms of bit capacity and data rates. We expect that as a result of current development efforts in materials and components, data storage capacity will approach 1 terabyte, and that transfer rates of 1 gigabit per second can be realized in the next 2 to 3 years. But it will be of critical importance to optimize the overall performance of the system through an integrated approach considering manufacturing, management, and cost issues, in addition to the technical issues discussed here. In summary, we have demonstrated the first digital holographic data storage system by storing and retrieving color images, sound, compressed video, and binary source files. We have analyzed the performance of the system to chart a course for future improvements through component optimization and system modeling. This first implementation was possible because we took advantage of the digital aspects of the data, bringing to bear the power of digital signal processing. As a result, we were able to study the trade-offs required to optimize storage capacity at a required bit error rate and at a particular data transfer rate. Innovative solutions allowed us to overcome past roadblocks, but much work remains to be done before a commercial system can be built at low cost. We believe, however, that the current results allow us to design and build a small, rugged, compact test device within a short period of time.